peux parfaitement reprendre la main. Merci.
Rosé, je prends cette place. Oui. Oui.
Should I start? Okay. Okay, so good morning, everyone. Please let me start by thanking the organizers for their kind invitation. Well, kind and not so kind, because what they prepared for us is really tough. So I'm joking. So the title of my lectures is Structure Formation in a Cosmological Context. So it's extremely huge topic. So I will try to do my best and to cover some aspects that I believe are important in the context. Obviously, this is very subjective. I prepared a series of 4 lectures. We will see how it will go. Maybe at some point, given the time, I will decide to skip some parts. But please don't hesitate if you are interested in whatever topic that either I discuss or I don't. Come and see me, discuss with me. I'm staying until the end of this week. Okay? So, sorry. Let's start from the very beginning. So, since essentially the beginning of the scientific era, one of the main goals of astronomy essentially was to map this uneven distribution, or to map the universe, or to understand the universe and map the universe we live in. And probably one of the major leaps towards this goal was to connect this uneven distribution of stars seen in the night sky with the 3-dimensional structure of the galaxy we live in. And the first published example of such an idea is this sketch. So this is the map of the Milky Way made by William Herschel in 1785. And Herschel, together with his sister Caroline, also made a really extensive catalogs of what was at the time called the nebulae that revealed an extreme diversity of this object, which naturally led people to wonder what these were. And it was William Parsons, an Irish astronomer, who is said to have built what was at the time the biggest telescope in the world, with the motivation to understand whether this nebulae, such as the one he sketched himself, could be some sort of island universes similar to our own Milky Way. Obviously, at the time, no one really understood that these nebulae were, in fact, the external galaxy to our own. And still, at the beginning of 20th century, there was an ongoing debate among scientists over the size of the universe and the nature of these nebulae. So one group of scientists believed that our galaxy was extremely big and it contained all the observed objects, while others believed that our galaxy was much smaller and all these nebulae were sort of external to it. And probably you know, in 1920s was held the debate, famous Gray debate, opposing 2 prominent scientists of the time. Harlow Shapley argued for this one big galaxy, whereas Heber Curtis argued that our galaxy was much smaller and all these nebula were external to it. And so this debate was settled in the mid-1920s thanks to the observations of redshifted nebula, thanks to Vesto Slipher and Edwin Hubble. And this conclusively proved that all these nebula had to be external to our own galaxy and that the universe is probably large enough to contain millions of them. And less than 100 years later, it was again a pure human curiosity that allowed us to understand that our universe in fact contained probably 100 billions of galaxies and that we occupy only tiny space in it. And it was exactly in 1996 when the Hubble Space Telescope, which was the most powerful telescope at that time, was pointed into the region of the sky that contained nothing really interesting in particular. But only after a few days of collecting photons, the processed image that is known as a Hubble Deep Field revealed something like 3,000 of galaxies, and it allowed us for the first time to see, for example, galaxies as they were when the universe was only 1.5 billion years old. So, you know, scientists, they repeat things. So they did it again in 2004. This time they pointed the Hubble Space Telescope with improved detectors into a region of the sky where is Orion constellation. And what came out, you don't see it very well because of the light, but it's this very beautiful picture called the Hubble Ultra Deep Field, which revealed something like 10,000 of galaxies, like really almost each point is a galaxy, showing their huge diversity in terms of sizes, colors, shapes, morphologies. We were able to see how galaxies evolved by interacting and merging. It revealed plenty of examples of galaxies that were already fully formed when the universe had only 40% of its age, such as, for example, these very nice disk-dominated spirals, these bulge-dominated ellipticals, or even this slightly perturbed Bayer galaxy. So as you know, I'm pretty sure you know, today it's James Webb Space Telescope, Hubble's successor, that continues this sort of legacy with improved detectors, with improved sensitivity, angular resolution, and so on and so forth, that is hunting the really first galaxies, first objects that formed in our universe. In the meantime, it's also showing really beautiful images on the galaxies, such as these nice spirals at slightly lower redshift, or maybe, you know, barred galaxies. So these are spiral galaxies with this central structure in the middle, showing their relative abundance up to redshift of something like 3 or so. So, so far, all of these images that we were taking occupy really a tiny space or tiny area on the full sky. So it's something like 2.5 arc minutes in size. So this corresponds roughly to 0.003 square degrees. But what we can do in order to observe a much larger portion of the sky, we need to zoom out. And we can use large galaxy redshift surveys that allow us to map the distribution of galaxies over a much larger area on the sky. So here's an example from 2DF Galaxy Redshift Survey, which allowed us to map the three-dimensional position of galaxies up to redshift of about 0.2. And it was essentially the first survey that allowed to do this measurement for more than 100,000 galaxies. So it was really a technological leap in this kind of attempt in astronomy, astrophysics to observe these galaxies. So we are sitting in the center. What we are looking at is the light cone. Every dot is a galaxy. And what you can clearly see just by eye is that galaxies do not form a Poisson set, so they are not distributed randomly. But they try to, or they are organized in the structures that are these overdense node regions that happen to be at the intersections of these anisotropic filamentary lines. In between, we can find the voids. And so all this is a so-called cosmic web, but we will return to this later. There is another very nice picture of the, well, you really can't see it very well, taken by TUMAS survey. So this one is this time full sky. So if you can see something, again, each dot is a galaxy. So it's about 45,000 of galaxies in a very nearby universe. So it's roughly the distance of 120 megaparsec. But even so, you can still see how this nice network, cosmic web network, stands out and emerges. But there is another very famous full sky picture that I'm sure you all know. It's this picture of the microwave sky taken by the Planck with the Milky Way in front. So if we do some magic and we remove this foreground, what comes out is the very well-known cosmic microwave background. So cosmic microwave background is essentially believed to be a first baby picture of our universe, and it imprints all the perturbations that were generated in the early universe that have seeded all the structure that we see today, that is planets, stars, galaxies, galaxy clusters. that evolved through the gravity in the expanding universe. So, of course, Planck was not the first one. There were Kobe and WMAP before that studied in details cosmic microwave background, but the Planck did that in very high precision and across a really large range of frequencies. And it measured this fluctuation of the temperature that are at the level of few in 1 million. And essentially, these are temperature fluctuations. However, these colors really correspond to gravitational redshifting of the photons as they come out from these potential wells in the early universe. And potential is tracing the mass. So actually what we are looking at is a mass map in our initial universe. So this is typically characterized with this density, this fluctuation spectra that really allow us to connect this temperature fluctuation coming from the early universe, this temperature fluctuation that we measure today with this density fluctuation coming from the early, generated in the early universe. So how is all this connected? At the linear level, it's the 3D matter power spectrum shown here for different cosmological probes that span a large range of physical scales, so it's the inverse of this wave number, but also a large range of cosmic times. So, for example, the CMB, which was emitted at the redshift of about 1,100, down to these LRG, so luminous red galaxies, allowing to measure this power spectrum that corresponds to really low redshift measurements. So, of course, in order to put all these points onto this plot, they are extrapolated to redshift 0. And this solid line is the lambda CDM model with the Hubble best fit parameter, and we see that qualitatively it sort of fits the data quite well. That's what we call the concordance model. So we have this early stage of the universe, and all this evolution between the early times and today contains the full information about the structure formation model, and it's kept together with this underlying cosmological model. Therefore, it also contains the information about the energy content of the universe, initial conditions, all the astrophysics, nature of dark matter, and dark energy. So this lambda CDM model, it qualitatively reproduces our measurements. So, so far, there have been a few tensions. Maybe you know about them, H0 and S8 tensions, but nothing really challenging, but it might depend who you ask, really. So it seems like we have a good description of our universe. However, it's highly unsatisfactory. Why? Because it's a model of ununderstood physics. Okay, we don't know still what the dark energy is. We don't know what dark matter is, and that it's most part of our energy budget of the universe. Okay, so let's put all this together in this timeline of our expanding universe, where the size should correspond to the radius approximately of the universe. So our universe started in, relatively speaking, a very small size as a Big Bang. Then there was this period of rapid expansion called the cosmic inflation. Then roughly at 380,000 years after the beginning, there was the cosmic microwave background was emitted. This corresponds to the period when the free electrons combined with the protons, they formed the hydrogen atom, and the universe became transparent. So the photons were able to travel freely. The period between this recombination and the time when the first luminous objects form, it's called the dark ages. Then we have a formation of first stars, first galaxies, possibly first black holes that start to ionize the hydrogen in our universe. And that's when the period of reionization starts, and you will hear all about that during this week. In the meantime, the universe is expanding, structures are forming, they evolve. At some point, dark energy overcomes the gravitational force, and this prevents formation of even larger structures. So again, when we look at the CMB, we are looking at the really particular time slice in our universe history. However, when we look at the structures on different scales, from largest to smallest, we really try to map the entire cosmic history of our universe, including this relatively recent accelerated expansion due to the dark energy. However, when we look at CMB, we are looking at the photons that come from almost perfect equilibrium with small perturbations. So this is difficult but totally solvable problem. However, for the rest, our data looks more like this. So it's really extremely beautiful, but it's also extremely complicated. So essentially, every data point is the result of highly complex, nonlinear physical processes. So usually what we do is to scan through the entire spiral as large as area that is as large as possible to record the position of the galaxies on the sky, and then measuring the redshift, which gives us access to their distance, so we have access to three-dimensional position of galaxies in our universe. But how do we go about modeling all this? So let me give you a sort of the brief sketch of how I sort of see we can proceed. So as every physical problem, we can split this one also into several steps. So the first one is identification of initial conditions. So we talked about the CMB, and that's from where we have parameters, our lambda CDM model, which is still the best one in terms of describing a large range of cosmological observations and having the least number of free parameters. And this is sufficiently good, and this is enough for our problem of structure formation. Then we need some ingredients. So we need to include all the physical processes that we believe are important for the formation of structures on multiple scales. And here it is really convenient to split this problem in two parts. One that contains only what I would call dark matter, which is we ask the question, how would structure formation proceed if we had only a dark matter? And then in the next step, we ask the question, how is this picture modified if we add on top of that also the baryons? So everything, all the normal matter, if you wish, everything that we are composed of, the stars, galaxies, and so on and so forth. Now, if we have initial conditions and all the ingredients, we can start to write our models. So different methods exist. One of the most robust, if you want to go down to the nonlinear regime, are numerical simulations, but other methods exist, semi-analytical methods, the so-called HOD, so high-level occupation distributions, and so on and so forth. Once you pick your favorite method, then you can make predictions. And these predictions can be compared with the observations across different scales. You can, in this case, test the predictions. But here I would like to stress that I see it as a double arrow in the sense that on one side, these observations can provide a feedback for the models that can be improved, but also these models can be used to interpret the data. Okay, so how does the structure formation proceed in lambda CDM or the CDM universe? So basic fact about the universe is that the structure formed hierarchically from small to large scales. And this is because the small scale perturbations are largest, so they grow fastest, and they form this gravitationally bound object. And this process of formation of bound object proceeds to larger and larger scales. So essentially on the largest scales are still linear today, so this perturbation on these large scales are still tiny. So we can nicely see it on these slices from the n-body gravity-only simulation, showing the three-dimensional matter in the logarithmic scale projected in these slices. So we see that on larger scales, we see a lot of structure. We see this nice filamentary network we saw previously with the huge nodes, dark matter halos at the intersections with the voids in between. But we also see that as we zoom in smaller and smaller scales, there is a lot of substructures. So there is a whole hierarchy of substructures, and these gravitationally bound substructures are called dark matter halos. So dark matter halos are well defined over those regions in our universe. They are composed of dark matter, but also of baryons. And their importance stems from the fact that we believe that galaxies form and evolve inside such dark matter halos. So what we believe is that every galaxy is hosted by a dark matter halo of a certain mass, and we have an observational evidence for that. It comes from the dynamics inside the galaxies or dynamics of galaxies inside clusters from gravitational lensing, and all this point towards the fact that there is much more matter than what we can see, and this matter is much more extended. So you can think about galaxies as sitting at the center of these dark matter extended structures. That's where the term halo comes from. So these structures are highly nonlinear, but the question is, can we find some simplified model to understand at least the basics of this nonlinear structure formation? And there is a very nice picture, very simplistic picture, but quite intuitive, which is the spherical collapse model. So imagine sort of uniform, spherically symmetric piece of universe or the region, which represents a background universe, if you want, and we cut out from that a spherical region. So it turns out that we can describe the evolution of this spherical overdense region using the same cosmological approach as for the background. So it will be the same space-time with slightly different cosmological parameters, namely it will be spatially curved. So we can write down the Friedmann equations for this region. And so here R is the physical radius of this sphere, so it's just proportional to the scale factor. So, and when you do the math, you come up with the two parts in this equation. So the first one is the classical Newtonian term, is the second order, so the evolution of the radius of this sphere of the mass enclosed in this radius r. And the second term is this lambda term that opposes this gravitational, so it's the repulsive force, it opposes the gravitational term, and it comes from the background. So we cannot solve it analytically in full generality, but if we drop the lambda term, there is an analytic solution, the parametric one, that corresponds to the semicircle. So you have probably seen that if you have taken some cosmological classes or courses. And so essentially what happens is that this shell at the beginning just expands. So it expands with the background universe. At some point it reaches what we call the turnaround. It's the maximum radius where the velocity is 0, and then it starts to collapse. And formally, the time of the collapse happens at 2 times the time of the turnaround. So now what we can do, we can find out what is the overdensity of this spherical region. So to simplify things, we will consider Einstein-de Sitter universe as the background, which is a good approximation for almost every cosmology at really early times. So we can find out the overdensity as the ratio of the density in the sphere divided by the mean density. So if we plug in this solution, we obtain the general expression for the linearly extrapolated overdensity. And now if we ask the question, what is the value of this linearly extrapolated overdensity at the time of collapse, we get this number, which is a number to remember, 1.606, which is essentially the linearly extrapolated critical overdensity value for the collapse. So in the linear theory, the regions that have overdensity, linearly extrapolated overdensity of value 1.606 will have collapsed, right? So now you can ask the question, okay, is this still true for other cosmologies? Because here we dropped the lambda, we were in the Einstein-de Sitter cosmology. And it turns out that if you do it in generic way, this is a still very good approximation. It's weakly dependent on the omega matter. Okay. Now, this spherical collapse model is valid only up to the point of the collapse where the density is formally infinite. However, we are dealing with the dark matter, it's the collisionless matter, so these shells, as they will collapse, they will start to oscillate and they will start to interact and exchange the energy, and they will do what we call, they will virialize. So in the end, we know that we don't form these singularities or this black hole. What we form are these dark matter halos. So these are the virialized structures. So when we say virialized structure, what does that mean? It means that the condition of the virial equilibrium is satisfied. So you probably know this one is 2 times kinetic energy plus potential energy equals 0. This is the virial theorem. And we can use this one together with the energy conservation to compute what would be the overdensity of such a collapsed virialized dark matter halo. So we can start here by considering the moment of the turnaround, because there the kinetic energy is 0, so we have only potential energy. And at the final time, we use the virial equilibrium, and we find that the virial radius is half of the turnaround radius. So essentially, we expect that the radius of this virialized structure at the end will be half of the one at the turnaround. So what does that mean? It means that essentially its density will be 8 times larger. Okay? So we can compute what is this overdensity by the same approach that we used previously. So the density at the time of the collapse of this virialized halo divided by the mean density, and again in the Einstein de Sitter model. So here, as we said, and we saw here, it's this density at the time of the collapse is 8 times the density at the turnaround. And similarly, when we realized that the density scales essentially in every cosmology as scale factor power 3, and in Einstein de Sitter it's time to minus 2/3. We get that essentially the mean overdensity will be 4 times smaller. So we put these numbers in, and we come out with a number which is close to 200, so another interesting number to remember. So this is the overdensity, essentially, of the collapsed object. So again, this was in a very simplified cosmological model. If people computed this in all generalities, there are some fitting formula that describe the dependence of this virial overdensity on the content of the universe. But this is the one of the points, and probably you have seen it already. Very often people use the number 200 or 300, and that is why every time when you see some plots that or some figures where they plot the radius of the halos, typically they write next to the notation of R whether it's 200, 300, because people adopt very different numbers. Okay. Now, so we now understood sort of how the dark matter halos are forming, but now can we continue and use this sort of simplified approach to compute some of the properties of halos? So the easiest one is, can we predict what is the expected number of these dark matter halos in a given volume and in a given halo mass range? So this was... Okay, so this is a little bit of a summary. So we just learned that according to the spherical collapse models, regions that have an overdensity that is larger than this critical overdensity will have collapsed to produce this virialized dark matter halos. Now, Preschechter came with the ansatz to compute the halo mass function, and this ansatz is that the probability that this overdensity field that is smooth on the scale corresponding to the mass m, this probability is larger than this critical overdensity for the collapse, is the same as the mass fraction that is contained in the mass halos with the mass larger than m. So this is, take it as an ansatz. So what does that mean? If we take a Gaussian random field, we can directly write this probability that this overdensity at the scale of m is larger than the critical overdensity for the collapse. And it's 1/2 of this complementary error function. And if we take this ansatz, we can directly write that this probability of this collapse equals to the mass fraction that is contained in the halos with the mass larger than m. But the problem is that in the limit where these RMS fluctuations go to infinite, that is when the m, so the mass of the halos, go to 0, this complementary error function is 1. So we get that only half of the matter in the universe is locked up in collapsed halos. So at the time, there was a very neat solution, multiplied by factor 2. So this is called a fetch factor. So later on, it was properly derived using the excursion set formalism. But at this stage, we will stay with this solution. And so we can go on, and now we can really write, using these ansatz, what this fraction would be. And now we are ready to write what the halo mass function should be. So we will define in this Preschechter formalism the halo mass function. This n is the number of halos per unit volume in a given mass range, so between m and m plus dm. So we can write it as this derivative of this fraction with respect to the mass. And to get the total mass, we need to multiply it by just the mean density. And so if you do a little bit of math, you can try it as a homework if you don't want to go swimming. You end up with this expression for the halo mass function with the exponential cutoff at high masses and the power law at the small masses. Okay, so this was relatively simple. How does this compare with the measurements of the halo mass function in numerical simulation, which follow properly this nonlinear evolution of structures? So here is shown an example of halo mass function. It's a weird unit, so it's sort of a multiplicity, but think about it as a halo mass function, as a function of halo mass in the Millennium simulation. So the symbols are the measurement from the simulations, and these dashed lines are the predictions from the Preschechter formalism, shown at redshift 0 and at redshift 10. So we see that at low redshift, at redshift 0, so at the mass of around 10 to 14 something, it's sort of okay. But at lower masses, the Preschechter formalism overpredicts the number of halos, whereas at higher masses, it underpredicts the number of dark matter halos. And this difference is even more dramatic at high redshift. At high redshift, it underpredicts the number of halos by order of magnitude almost at all halo masses. Now, I was mentioning that there are other techniques that improved on the Preschechter formalism by considering not spherical collapse, but ellipsoidal collapse. So here is another simulation, a Bolshoi simulation in these large boxes. Symbols are again showing the measurements from the simulation, and the lines this time show another approximation, that it's improved approximation considering the ellipsoidal collapse. So we see that at low redshift, this sort of nicely follows or reproduces the measurement, except at low masses where even this formalism overpredicts the number of halos, small mass halos. Whereas at high redshift, it overpredicts them at all halo masses. Okay, so it's not perfect, but it's better. So we have a sort of a theoretical handle also, and we understand how these halos form and in what numbers they are expected to form. Okay, another important property of dark matter halos is their angular momentum. So dark matter halos acquire angular momentum due to the tidal torques from the neighboring overdensities. Again, we can write in the linear regime, it's called the linear tidal torque theory, this angular momentum of these proto-halos is proportional to the misalignment between the inertia tensor of the halo, the region that will collapse and form the halo, and the tidal tensor of the surrounding matter. Now, okay, so just a few words about that. So the tidal torque theory predicts that this angular momentum will grow gradually until the turnaround, and then it should stop evolving, and this is essentially because the inertia tensor will decay very quickly. However, it was seen in the numerical simulations that it is not this linear tidal torque theory is pretty good, but it fails because it is not able to predict the angular momentum of individual halos. So it's pretty good in the statistical sense, but it doesn't work for individual halos. Why? Because it doesn't capture the growth of the angular momentum from the turnaround and the collapse, where it was seen that there is a substantial growth of the angular momentum of halos, but also it doesn't capture its evolution after the collapse. So the halos will evolve, their angular momentum will evolve due to the interactions with other dark matter halos, due to the accretion of the material from larger scales. But it's a sort of good approximation and good starting point for any extended theory. So now, this angular momentum is very often parameterized by this halo spin parameter. There are different definitions of that. That's not the main point. But the interesting thing is that when people measured this probability distribution function of this lambda parameter, they realized that they follow the log normal PDF distribution with the mean roughly around 0.03 for very different cosmological models. So what does that mean? So very low value of this spin parameter means that these flattened dark matter halos, they are not supported by rotation, but rather anisotropy in velocities. So just for your information, this lambda for the spin parameter for a nice rotating disk would be of order of 0.4 or something like that. So you see this difference. And it doesn't seem to depend on mass or on the underlying cosmology. We have seen that dark matter halos contain a lot of structures, but we can still compute sort of spherically average profile. And that's what Navarro, Frank, and White did in 1997 with a series of different n-body simulations with slightly varying cosmologies. And they found out that regardless of mass and regardless of this cosmological model, all these halos seem to follow this double power law profile with a slope of -3 at large radii and the slope of -1 at small radii. So this profile is now called Navarro, Frank, and White. It's still a little bit, I mean, this is sort of surprising, right? Because if you think about the formation of dark matter halos, there are different possible ways they can form. Some halos can form very quietly, just by accreting the matter. Others will form through sort of violent mergers or interaction. So it's sort of surprising that they would have the same profile. And essentially, this profile is fully characterized by two numbers, so the virial mass or the virial radius, they are equivalent. And this concentration parameter, which is just ratio of this outer radius, so the virial radius, and the scale radius, this RS, which is essentially the radius at which this logarithmic slope is of -2. Now, what was also measured in these cosmological simulations is that the concentration is correlated with the formation time of the halos. That is, halos that form early tend to have higher concentration. So it seems sort of understandable. Halos that form very early on, the universe was much denser, things were much more compact, so the concentration was higher. But we also know that the early forming halos had a lower mass, right? So we expect that the concentration should be anti-correlated with the halo mass, and that's exactly what was found in the numerical simulation. The scatter is quite important, but the interesting thing is that at the fixed halo mass, the concentration is still correlated with the formation time of the halo. So now, since then, there have been several models attempting to explain the dependence of the correlation between the concentration and the mass and the redshift evolution. Essentially, some models are able to go back to initial density field and connect this concentration with the height of the peaks in this density field generated in the early universe. But the most important point is that they all agree in the sense that at fixed redshift, this concentration decreases on average as the mass of the halo increases. And at fixed halo mass, the concentration decreases with increasing redshift. So it's a sort of basic fact about the dark matter halos. Now, one thing to point out is that this inner part, so this inner slope of the dark matter halos, is still very controversial. So already at the time when Navarro, Frank, and White came up with their model, there were other people that came with different profiles because they measured slightly steeper profiles. This is a sort of Moore profile. And then observations suggested that this slope or that this density profile in the central regions is very flat. And so indeed, it seems that the data, so it's showing here with the error bars, you have the data. It seems, and you see the very different models, so it's very hard to disentangle. But it's sort of, maybe in the community, at least on the observational side, there is an agreement that it's the so-called ANASTO profile that reproduces much better the data.
Why do you produce so similar results at around 20 parsec and 7?
Well, this is, keep in mind that this is just an you mean why those curves...
Why do all of the models produce very similar results?
Well, it depends. So this is the circular velocity, right? So it depends. You have to look at